Hi, in this video we're going to look at some shortcut rules for the derivatives of the 6 trig functions. It's important to remember that all of the shortcut rules that we're learning right now come back to basically what happens when we apply this definition right here to whatever function we're working with, or maybe combination of functions that we're working with. The whole point of those shortcut rules, though, is that once we've done this once for this sine function, then we could remember what we got so that we don't have to go through that process every single time. So we're going to go through this process with this function. We're going to just do what the definition says and kind of churn through it. There are a few hints here, trig identity, and a couple of special limit reminders that we're going to need from earlier this semester. Alright, so I'm just going to scroll up a little bit and we'll go through this derivative. Okay, so for our function sine of x, our derivative, our f prime of x, is going to be, I'm just going to write down the limit here. Limit as h approaches 0, f of x plus h. This should be familiar. We've been doing this for a while, all over h. Okay, and then we're going to do that with the sine function. So I'm going to put x plus h inside the sine function in place of the input, and then minus the original function all over h. Okay, sometimes students are tempted to try to distribute a sine function through the parentheses, but it doesn't work that way. There's a little reminder up here of a trig identity about how that actually works when you have sine of a sum of two angles. So we're just going to apply this identity to what we have right here. So I'm going to have the limit as h approaches 0 of, I'm just using the identity, sine of x times cosine of h plus cosine of x times sine of h. Alright, so I just applied that identity to the sine of x plus h. So that's what I have right here. And then on the numerator, I still have minus sine of x all over h. Okay, so when we did some of these problems before, we had a lot of canceling that happened at that point. But there are a couple of other hints up here in the bullet points that maybe help you kind of see what might be happening. There's a couple of special limits that we had before that we're going to actually end up using here. So we're going to have to do a little bit of algebra, some rearranging, and what I'm after is basically trying to get those special limits here without violating any rules of algebra. So I'm going to scroll up and do that. Okay, so I do have a sine of h over h factor here, so I'm going to kind of split this up a little bit first of all. So then I'm going to take the term that says cosine of x times sine of h, and I'm going to separate that from the other two terms that are on the numerator here. So I'll have cosine of x times sine of h all over h, and then I'll have separately, as a separate fraction with the denominator of h, the other two terms, sine of x times cosine of h minus sine of x. Alright, so I've got the limit as h approaches 0 of all of that. Part of why I did that was that I looked at these two hints up above and I was trying to get this special limit. We've got h approaching 0, not x approaching 0 here, but I've got that sine of h over h form in that first one. Then there's another special limit up above, so you might notice that on the last term in my brackets here, I'm going to rewrite this first part here as cosine of x over 1 times sine of h over h, just to kind of separate that sine of h over h special limit out. And then I might notice on this next term here that if I factor out a sine of x, I'm left with cosine of h minus 1, and I have the whole thing over h. And that's basically the form of that other special limit. So I'm going to separate that last term out here, and then I think we will be ready to evaluate our limits and find our answer here. Alright, so in this last term here, I'm going to separate that also and write sine of x over 1 times the other part here that would be the special limit that was up in the hints in the bullet points above. Okay, so I had two special limits here. This one, and those are here and here. Remember, h is what's approaching 0. And then these other functions that I have in here don't involve h. They involve x, not h. So when I let h approach 0, they're going to stay the same. So I'm using some theorems about limits here to finish this, but basically I get cosine of x over 1. There's no h there. So as h approaches 0, that part just stays cosine of x over 1. And then the limit as h approaches 0 of this first special limit is 1. And then in the second term, the sine of x over 1 just stays that. There's not even any h's there. And then the second special limit that I've circled there, if we look in the hints up above, that limit is 0. And then if I just simplify all this, looks like what I get here is just cosine of x. Okay, so what that tells us is that I don't have to go through this anymore. If I can just memorize that the derivative, I'm going to write it over here, the derivative with respect to x of sine of x is cosine of x, then I don't have to go through this every time. And so that's probably easier. Memorize that derivative, and then we don't have to go through this. Okay, so we're going to go through this with the cosine function and one of the other trig functions, but the basic idea is that they all kind of work the same. There's some different trig in the middle, maybe some different trig identities, but essentially they pretty much all work pretty much the same way. So, all right, we're going to do next the cosine function and figure out what the derivative of that function is using that same limit definition. There's this different trig identity. We'll use the two same special limits we had before, but all right, so here we go. F prime of x equals limit as h approaches 0. All right, this time I'm going to go ahead and not write this definition down. It's right up there. We're going to just go ahead and do what it says here. Plug the x plus h into the cosine function, and then minus the original function, cosine of x, all over h. That's just applying that definition to the function we're working with. And then we've got the trig identity that we're supposed to use. We're going to use that on the cosine of x plus h. So we'll have limit h approaches 0. Be careful with all the functions in the trig identity here. Cosine of x, cosine of h, minus sine of x, sine of h, and then I have that minus cosine x term on the numerator, all over h. Okay, and again, just like the last one, we're going to do a little bit of rearranging. I might notice I have that special limit form here again as h is approaching 0, so I might try to rearrange some things just like we did in the last one. Okay, so this, I'm going to separate that whole term, that minus sine x sine h all over h. So I'll have minus sine x over 1 times sine h over h, and then plus, and then on the other two terms that I have here, so that would be the cosine of x cosine h minus cosine x, I can factor out a cosine x. So cosine x over 1, and then I'm left with cosine h minus 1, and I don't want to forget that denominator of h. Okay, so I skipped a couple of algebra steps in this one that I wrote out in the previous one. If you want to go back and look at that previous example a little bit more and kind of be sure you're clear about the algebra there. But then from here it's pretty much the same way. I've got this special limit, which is 1. And this special limit, which is 0. So from here, we basically just apply those, and I get negative sine x over 1 as h approaches 0. That just stays what it is. This special limit, that's 1. And then cosine of x. And then this other special limit, that's 0. So I get negative sine x. Okay, so we just showed, and if we just memorize it, we're not going to have to go through this every time, that the derivative with respect to x of cosine of x is negative sine of x. So memorize that one too. All right, we're going to do one of the other 4 trig functions. I'm not going to do all of them, but we're going to just do one more. We'll do tangent here. All right, so I could try applying that same definition to the tangent function and use some trig identities and get there too, but actually if you remember, tangent can be rewritten in terms of sine and cosine, and so I don't really need to do that. If I remember my derivatives for sine and cosine and remember quotient rule, I don't actually need to go through that limit definition here. I can use the ones I already showed together with quotient rule. Okay, so our derivative, f prime of x, is going to be, I'm going to write out some hints here about quotient rule in case you've forgotten some details of quotient rule. All right, so I'm going to set up some parentheses here. The derivative of the top, or f prime, times the bottom minus the top times the derivative of the bottom all over the bottom squared. So if you can write that out, whether you remember it in terms of F's and G's or U's and V's or lows and highs or tops and bottoms, as long as you can write out the quotient rule correctly, then it's just a matter of applying that. Okay, so there are a couple places where I'm going to need to remember those derivatives that we just did. So when I go to take the derivative of the top, which I'll fill in this first spot here, I need to remember that the derivative of the sine function is cosine. We did that just earlier in this video. We showed that using that limit definition. All right, so the derivative of the top and then times the bottom, that's just the bottom function from my original f of x quotient, minus the top, that's just the top function, times the derivative of the bottom. Okay, so in this second parentheses here in the second term, I guess last parentheses on the numerator, I need to remember derivative of cosine from what we did earlier in this video. So derivative of the cosine function is negative sine function. So those two things I highlighted are the derivative of the top and the derivative of the bottom, but I've plugged that all into quotient rule here. And then the other part of quotient rule, I'm going to put the whole thing over the bottom function squared, or the cosine function squared. All right, at that point I have the derivative. It's just a matter of cleaning things up and tidying this up. On the numerator, I have cosine of x times cosine of x, which is cosine squared of x. And then I'll have a minus sine of x times a negative sine of x. So negative times a negative will be plus sine squared of x. And then the denominator is cosine squared of x. And there are several different things I could do with this, but the easiest thing to do is to recognize that I have on the numerator here a trig identity. And so maybe you remember that as hopefully the one trig identity you know if you don't know any others. It's Pythagorean identity. Cosine squared theta plus sine squared theta is 1. So I'm going to use that trig identity to simplify the numerator. So I end up with 1 over cosine squared x, or most students, and in our textbook, they'll usually rewrite that as secant squared of x. For this one, I didn't use the limit definition of the derivative. I used the results I got from doing that limit definition before, and then quotient rule. But again, this is one to memorize. The derivative with respect to x of the tangent function of x is secant squared of x. So memorize that one. All right, and then so we've done 3 of the 6 trig functions. So the other 3 essentially work pretty much the same way. You can rewrite cotangent as cosine over sine. You can rewrite secant as 1 over cosine, and cosecant as 1 over sine, and then just apply quotient rule to that. All right, and so when you get done with all of that, you end up with some derivatives here. So you want to make sure that you memorize these that are in this chart. Flashcards are a good idea, or just make a chart like this and then fold it in half and practice writing the derivative of each function. One thing that you want to be super careful about, every once in a while I see students that will write silly things like this. They'll write things like tangent of x equals secant squared x. And what they really mean is that the derivative of tangent of x equals secant squared x, but this statement that's right here is not true. So don't write things like that. That's nonsense. Instead, write things like this. The derivative of tangent of x is secant squared x. The key thing, just like here in this chart, we have a function, and its derivative. And in general, the function and its derivative are not equal to each other. They are related to each other, but they are not equal to each other. I know that might seem like a silly, picky little detail, but really, if you're not careful about things like that, you get sloppy with your thinking, and then you end up with wrong answers just because you were thinking about it in a weird way. So be careful not to write things like that. Instead, use correct notation, either like I have in the chart, function and derivative. So one is f or y for the original function, and then the derivative, f prime or y prime or dy dx. So using proper notation for function and derivative. Or the way I have it written down here, derivative with respect to x of tangent of x is secant squared x. All right, we'll do some examples in the next video where we use these derivatives to find derivatives of other kinds of functions.